So what I want to talk about today is what we have learned from the microwave background and observations of the universe's large-scale structure. So begin by giving you a sense of, I think, what we've done over the past 20 years, turn to where we are today, and then look to the future. And to give you an overview of the talk, what will be the theme is, up to about 2 years ago, I would say that all the pieces were fitting together nicely, observationally. We were left with these deep mysteries that I very clearly require physics beyond the standard model, dark matter, dark energy, or understanding the universe's origin and physics of inflation if it didn't indeed occur. Show how data in the last year has been very intriguing in that we're really starting to see really quite significant tensions between different sets of observations. And that these tensions likely point to systematics in the data, but could potentially be the sign of new physics. And then look forward to a series of observations over the next several years, and observations in which IPMU is playing a significant role, that have the potential to clarify the situation. Before doing that, I want to say a little bit about the second half of my institutional orientation, the Flatiron Institute. And in doing so, say that imitation is often the highest form of flattery. And it was a pleasure to play a small role in helping to get IPMU going. And now what I've been doing over the past year is helping to build a brand new institute in New York, the Flatiron Institute, that's been funded by the Simons Foundation. It's an institute that will grow to be about 250 people in 4 centers: a Center for Computational Astrophysics, which I lead, a Center for Computational Biology, led by Leslie Greengard, a Center for Computational Quantum Materials, led by Antoine Georges, a 4th center whose focus we've not yet established. These centers all build on the idea of the centrality of computation in its various roles to advancing science in different forms. So we will have a scientific core made of computer scientists, applied mathematicians, that will provide a link between all the centers. Our own Center for Computational Astrophysics will look at sort of what I think the 2 powerful ways we're using computation. One, going from initial conditions forward and looking ahead to the LIGO announcement. That means things like solving the equations of relativity, looking at solving the equations of neutron star physics, but also going from the observations backwards, using powerful statistical techniques to infer novel things from large data sets. So, we will have among our group leaders will be Will Farr, who will be joined with Stony Brook, who's played a major role in the LIGO analysis, and Yuri Levin, who's done a lot of important theoretical work related to LIGO, who will be joined with Columbia. So among the many lessons I've learned from IPMU is the importance of making these joint appointments, the importance of having very strong ties with the surrounding community and more broadly internationally. And can only say that I hope when we reach our 10th anniversary, we've just had our first, that we can look back at the level of success that IPMU has achieved and hope that we'll have achieved something similar. Let me now turn back to the topic of my talk, the strange universe we find ourselves in. Let me just remind you that what we've learned is that a simple model with a handful of parameters, the age of the universe, the density of atoms, the amplitude of fluctuations, how they depend on scale, and the density of matter, basically those 5 numbers, together with a measurement of the optical depth of the universe, is able to basically describe a host of astronomical observations. And while this model is simple, it also implies that we absolutely need new physics, dark matter, dark energy, the physics of inflation, and all of those new physics lies beyond the standard model of physics. It's all requiring something new. Let me also just remind you of our basic cosmological model. In the basic model, the universe starts out very hot, very dense. It expands about 380,000 years after the Big Bang. The universe becomes cool enough that electrons and protons combine to make hydrogen. When we look out the microwave background, and I'll be showing you some microwave background data, we're basically looking out at physical conditions at that point, about 380,000 years after the Big Bang. The microwave background is also affected by subsequent events like star formation, which reionizes the universe, and the large-scale distribution of matter around galaxies, which give rise to fluctuations. But in detail, the basic picture is you should think about looking back in time, looking back to when the universe made its transition from being ionized to neutral. This is soon after it made the transition from being completely dominated in its energy density by radiation to being dominated by matter. Now, we'll be looking at the cosmic microwave background in detail. I just want to remind you that overall it's remarkably uniform. If you could look out with eyes in the microwave, you would see the same temperature in all directions with a temperature of 2.73 Kelvin. And it took a long time, actually, from after the discovery of the microwave background to when the first fluctuations were seen by the Kavli experiment. And to orient you, we're looking here at a map of the whole sky. You should think about this as taking the sphere around us, projecting it onto the sky. This is the galactic south and north pole. The bright red thing you see across the center is not anything cosmological. It's our own galaxy. And that's a mission of radio emission from synchrotron, emission from dust. As a cosmologist, I like to think of this as I'm looking out at from the top, the view of a building, a high tower. I'm on, top of the Empire State Building in New York, looking out at the surroundings, and there's a lot of smudge, just some dirt on the window, and I've got to look through the dirt on the window. And the galaxy is the dirt on our window. My galactic astronomer friends don't like thinking of themselves as the smudge on the window, but for a cosmologist, that's what they are. My own involvement in this comes primarily from initially from my work with the Wilkinson Microwave Anisotropy Probe, a NASA-led mission that we launched out to the L2 point, about 4 times the distance of the moon. There's my colleague David Wilkinson, late colleague David Wilkinson, who we named the mission after. And just want to go through quickly what the sky looks like, just to remind you that we have to deal with this pesky galaxy. And this is why we need multi-frequency data. And you can see we combine data at all these different frequencies, and only after subtracting that off can we construct a clean map of the universe. And here's a clean map of the sky, and written on the clean map, for some reason, is Stephen Hawking's initials. So what do? We throw down circles like that around the sky. We measure the variance as a function of scale. This translates to an angular power spectrum. And this shows the measurements, and I'll show more recent data with more detailed measurements, but already, this is now a decade ago, back when IPMU was set up, we had data that looked like this, where we could measure the amplitude of fluctuations as a function of scale. You can see the excellent fit that the now standard cosmological model, the lambda CDM model, provides to the data, and that we could then fit that data, then turn to our computer simulations, run simulations of galaxy formation, where we start from those smooth fluctuations, evolve them forward in time, predict how the lumpiness should evolve, measure the large-scale distribution of galaxies with things like the Sloan survey and get a consistent picture. And we see a consistent picture with a host of astronomical observations. So we can infer the density of atoms by looking at the height of the acoustic peaks in the microwave background. We could also infer the density of atoms by looking at the abundance of deuterium. They both determine the same thing with an accuracy of 5%. For me, and this is now 14 years ago, I remember getting an email the day before we put out the first WMAP release from David Teitler from UC San Diego that said, I know you're about to release your results. I want to not have appear that our results were affected by yours. Our paper's coming out in 2 months. Here's our best measurement of the deuterium abundance. This implies a baryon density. It's about 5% of the critical density. We already had our measurements providing this, which also gave that same number within 1 sigma. You can determine the abundance of density of atoms from looking at deuterium, a fossil produced in the first 3 minutes of the Big Bang, looking at the abundance of atoms by looking at the behavior of acoustic waves 380,000 years after the Big Bang. And I think the agreement between the two of them represents to me one of the really important tests we have of our standard model of cosmology. And we also get a mostly consistent agreement on Hubble constant. I'll talk a little bit more about that as my talk goes on. Measurements of age of the universe from stellar evolution, large-scale clustering, gravitational lensing, all the pieces broadly fit together. And this represents, as and I'll show a bit, one way of looking at the data is we can look at how lumpy the universe is, the RMS fluctuations and density matter fluctuations as a function of scale. And over 10 to the factor of 10 to the 10 in mass, we see consistency between our observations, the points, and the prediction of a lambda CDM model. A model which in this case effectively has one free parameter to fit the data, which is the break in that spectrum, which is determined by the horizon, the mass within the horizon when the universe made its transition from being radiation dominated to matter domination. The next big step forward in microwave background measurements came from observations from the Planck satellite, an ESA-led mission with significant NASA participation. And what Planck did was again map the whole sky, and this shows the WMAP data and the Planck data, and at the resolution of this projector, the two data sets agree beautifully. What you can't see here is Planck actually has a much more detailed picture. We can zoom in, it takes too many pixels to fit in the screen, but we'll look at this when we look at the power spectrum. Let me just remind you of what we do. We take the sky, we expand it out in spherical harmonics. We show that there seems to be no preferred direction, no preferred axis. Therefore, all the information is contained in the angular power spectrum. Actually, more remarkably, when we look at the primordial fluctuations, everything's in the angular power spectrum. We can take the 4 million independent points measured by Planck, reduce all the information to an angular power spectrum that completely describes the observations. We see no evidence for any higher point statistics. And then, of course, fit that with the simple model. And what I'll show on the plots is this, what we call decibel, which basically corresponds to the variance on that angular scale. Again, stressing that we see the same sky, and when you look quantitatively, multiple by multiple, this shows the cross power spectrum between Planck and WMAP in the black, the Planck auto power spectrum in the red. And the takeaway you should have from this is twofold. One, where they can measure an individual multiple on angular scales larger than about 1/3 of a degree, where they both measure it with high precision. Planck and WMAP see the same sky, they measure the same thing. It's really a beautiful confirmation. There's two independent experiments seeing the same thing. And you'll notice the error bars get a lot smaller in red than black. Planck was a step forward. It measured things with higher precision. We see the same thing when we go to smaller scales. This is now comparing observations with the Planck satellite on the bottom. This is a patch of sky measured by Planck with measurements taken from Chile with the Atacama Cosmology Telescope shown above. And we show two different frequencies where they have comparable measurements. And we could also look at this quantitatively when we look here at measurements from WMAP in blue now on large scales, from ACT in green, from the South Pole Telescope in red, compare them with the Planck measurements, and you can see, I think, two big high-level takeaways from this. One, all the experiments broadly agree at this level in their measurements of the power spectrum. And two, that the theory, the blue line going through this, does a rather good job at describing what's going on. You know, the way I think about what we're seeing with those peaks is fundamentally we're seeing acoustic fluctuations. What's going on in the universe, say we looked at the universe at redshift 10,000, we have adiabatic fluctuations in the density of electrons, protons, photons, dark matter. What do I mean by that? Regions that have more dark matter have more electrons, more photons, more protons. The number of photons per dark matter particle is constant over space. So this means let's create a delta function fluctuation in dark matter here. There's also a delta function fluctuations in baryons and photons. Extra photons and baryons mean extra pressure. What happens when I create a region of extra pressure? It sets off a sound wave. That sound wave propagates out. In our case, it propagates out for 380,000 years. You get a ring of excess photons and baryons around that excess piece of dark matter. All right, and that gives rise to basically everything you see in the microwave background. You can think of it as I've just described the Green's function of the fluctuations, of how you go from the initial conditions forward. That Green's function gives you a cold spot where you have extra dark matter. More dark matter means the gravitational potential is deeper, and the photons have to climb out of that potential. If you have extra photons, it's hotter. So what you expect to see is around every cold spot, a hot ring. And this is a nice analysis. It was first done by Ichiro Komatsu on the WMAP data, and then later done by the Planck team on their data. And this shows, let's see, the bottom is theory, where I take every cold spot I see on the sky and stack around every cold spot in the map what I see, and what's predicted is a hot ring. The data I see above. And this is the same stacking around every hot spot, and in between there are pictures of polarization. The lower panel is theory, the upper panel is data. This is just equivalent to showing the power spectrum, but physics happens in real space. And you can see dark matter is non-baryonic by eye, right? See that cold spot in the middle? That's the dark matter sitting there. The baryons and photons are out in a ring. If the baryons and photons and dark matter interacted, you wouldn't have that cold spot and ring. The depth of the cold spot compared to the height of the ring gives you a direct measurement of the baryon-photon ratio, a baryon to dark matter ratio. You just, that's telling you what the dark matter density comes from. By the way, the size of that ring is how far an acoustic fluctuation moves in 380,000 years. That's nature holding up a ruler to us. That's the acoustic scale. With that ruler, we can then measure the age of the universe, because we can measure the geometric distance to that, and that's where we get 13.77 billion years for the age of the universe, with an uncertainty about 50 million years. That same pattern of acoustic fluctuations shows up, and we'll look at this in more detail, not just in the temperature fluctuations, but in the polarization fluctuations. Here, this red line comes from fitting the Planck temperature data and then only getting the best parameters comparing it to temperature polarization in Planck and to polarization in Planck. And then the plot above shows measurements of the large-scale distribution of galaxies and shows that the large-scale distribution of galaxies show the same acoustic fluctuations. So we can look at the pattern galaxies make today, and by doing something like looking at the Sloan Digital Sky Survey, and compare that to what we see in the CMB. Here, these curves are what you predict based on the Planck data for the correlation function of galaxies versus scale. The points are the galaxy distribution. So what we see in the CMB predicts what patterns we see in the galaxy. And this shows from a series of different galaxy surveys. And the IPMU is part of these BOSS measurements. I believe these papers are Ihara et al., actually. The best measurements there. And if I were to summarize where we were a year or two ago, I'd say we have a consistent cosmology, and we know we need new physics. If I were to look at inflation, I'd say that the inflationary model is doing pretty well, at least on the observational side. There's some deep theoretical issues one has to solve to advance that theory, but let's just talk about the observations. We see evidence for a flat universe, superhorizon fluctuations, adiabatic fluctuations, and the Gaussian fluctuations, and the key remaining prediction is gravitational waves. And the idea with gravitational waves is we hope to look for the pattern of polarization by looking for the E modes and the B modes in the sky. We can take the polarization pattern we see, divide it into a pattern that's symmetric under mirror reflection, that's E modes, an anti-symmetric part that's B modes, and go from there. There was a lot of excitement a couple years ago when there was a claimed detection of gravitational waves. I think a lot of people were convinced by this rather compelling plot. This dashed line shows the predictions for what you would get if there was a gravitational waves from inflation combined with the signal of gravitational lensing. And these were measurements from the BICEP experiment. I was one of the people who was nervous when this came out. It's an interesting and longer story about how social media got me involved in this. I gave a talk at NY. I read the BICEP papers on the train ride in to give a talk at NYU a week after they came out. I knew I had to talk about BICEP. My talk wasn't quite ready. There's an hour-and-a-half train ride. On the train ride, I'm looking at the slides that they used for doing their analysis. And the key thing here is that if you want to understand whether or not you're seeing that beautiful image in the distance or muck on the window, you need multi-frequency data. BICEP didn't have multi-frequency data. So that's what they did was they took the Planck data, which wasn't public yet, but someone had given a talk on the Planck data where they showed this figure. And they downloaded the figure, they scanned the file, they read the intensity off the plot, and then did their analysis. Now, if you're going to live that dangerously, you need to read the whole slide. And they ignored the part that says on top, not CIB subtracted. They ignored the fact that they hadn't read the rest of the slide package, which said, the real surprise in the Planck data is dust is more polarized than we thought, that the polarization fraction is as high as 20%. You can then take the observed level of dust, say it's 10%, which isn't that surprising given it could be as high as 20%. And when you do that, you can fit everything. And it's turned out it's all a bit of smudge on the window. You can combine with Planck, you clean it up, the signal's gone away. So, the takeaway from afar, for those who are not following it, is we have not yet seen gravitational waves. We have been reminded of the importance of some care in analysis, the importance of paying attention to our galaxy. Now, fortunately, we can do a lot better, and the experiments are about to improve, and I think the most exciting big step forward on the horizon in this is LightBird. And this is an experiment that IPMU is playing a leading role in. It's a JAXA-led mission that will be a multi-frequency mission using a small satellite. It will be the third generation space mission after COBE, then WMAP, then Planck, and it has the potential to detect gravitational waves. So I think this is something we're all looking forward to. Before concluding, I want to give a sense of what's happened in the last year, and I think what's happened in the last year is increasingly interesting tensions. There's been existing tensions since the Planck results came out between the Planck measurement of the Hubble constant, about 68 kilometers per second per megaparsec, and the best measurements from the ground using local distance ladders, measurements giving values like 73 kilometers per second per megaparsec, work done by Adam Rees and others. When I was a graduate student, the idea that 68 and 73 was a tremendous tension would be shocking. People were arguing whether it was 50 or 100. We didn't know the age of the universe to factor 2 or maybe even 3. But now we're doing precise measurements. And these tensions in the Hubble constant are significant enough, if one believes the errors of the experiments, that it's pointed to something profound. Now, most likely it's still systematics in the experiments we need to get a better control under. But there's other tensions now that are emerging as well, and one of them that's quite significant is measurements of how lumpy the universe is, the amplitude of fluctuations. And again, these are things where the errors, the numbers themselves agree at first quite well, lensing measurements giving an amplitude close to what Planck sees, but when you include the error bars or look at the parameters, the discrepancies are interesting. And I want to focus in on, there's a recent, and I think somewhat confusing in the way it's presented, paper that just came out from the Dark Energy Survey, where they did a beautiful job, made, I think, the best measurements of optical lensing, measuring how lumpy things are. And then in the abstract of their paper, they talk entirely about how beautifully things agree. But if you take their data and take the DES data and compare it to Planck, the best fit model has W, an equation of state, of minus 1.3. It differs by 4 sigma from lambda CDM. Usually, if you have a detection that the universe is being ripped apart, and you have it at 4 sigma, you would think you would mention it in the abstract or conclusion. What they've done is they've reported, and this shows different combinations of the data, basically only in the abstract, which is I think what most people have read, the red points here, which is combining DES, Planck, baryon acoustic oscillations, and measurements of the Hubble constant. If you combine them all, it nicely goes back to about the standard theory. But let's say you just look at DES and Planck. That gives you that black curves. And these are plots of the amplitude of fluctuations, the matter density, the Hubble constant, the equation of state, the parameters in the model. And you'll notice that the red contours and the black contours differ by more than 2 sigma in a multi-dimensional space. My guess is they're off by about 4 sigma total. And these are 2 data combinations that are largely using the same data, right? It's DES and Planck in 2 of them. And if you just look at DES versus Planck, which is the green and the blue, again, the data sets marginally are consistent and they give you this funny result. So there's either a systematic in DES, in Planck, or there's something profound there. And we need to figure this out. And there's interesting things going on as the measurements of CMB on small scales improve. Over the summer, the SPT team released their most recent measurements with deep observations of a 500-degree patch. Those are the red points shown here. Broadly, it looks like they agree. And there's TT, and now TE. And it looks like the points all lie pretty much on the same curve. If you look, and there's EE. If you look carefully, the SPT points are all a little bit above or below the curve. What this translates to when you look at cosmological parameters in these multicolor Plano plots we like to look at is things aren't quite consistent. So let me just draw your attention to Planck is in yellow. SPT is in gray for the whole data set, red if you just look at high multiples. And you can see often in this multidimensional space, the red contours and the yellow contours at 2 sigma don't overlap. And this is a projection of a 6-dimensional space. So that means that, again, they're 3 to 4 sigma off at least. Unfortunately, neither of these groups did the calculation of how much do these differ when you look at the models. There's sort of a bit, I think, of a cultural problem we have at the moment, that everyone thinks the standard model fits and no one's brave enough to talk about deviations too much in these experiments. But here's the best fit values, and you can look at the values, say, of sigma 8 or the Hubble constant that you get from 2 separate CMB experiments. And they're off. So, well, where do we go from here? I think we need to get more data. And there's another number of steps we're taking. Right now, we've got data in hand from the Advanced ACT experiment. Our plan, by the time we finish in 2018, is to cover about most of the accessible sky from Chile at 5 frequencies. This is how well we hope to do with the overall spectrum. With the data we have in hand right now that we're analyzing, we should be able to get a measurement of, for example, the Hubble constant with error bars about the same as Planck. We'll do better with the full data set, but right now we should have measurements that are about as accurate. We overlap a lot on the sky, so we should be able to compare the maps kind of pixel by pixel and see if we see a consistent picture. And right now we're in the midst of, we've drawn up a pretty detailed plan of how we do this in ways in which we are mostly blind to what the Planck results are so that we're not swayed subconsciously by our desire to either confirm Planck or contradict it. So we're hoping, sort of on the year time scale, to have results there. Looking forward, we brought together a big collaboration that involves both the teams that have made up the Atacama Cosmology Telescope and the teams that have made up the Polar Bear Telescope, which has been led out of University of California and significant involvement here from KEK, with a plan to build what will be a series of telescopes, a large telescope which will be able to measure the small-scale fluctuations, and a number of smaller telescopes optimized to go after CMB polarization. Those aim to be on the sky around 2021, and building on the financial success of Chern-Simons theory, we have this funded. We're also going to see significant advances in measurements of large-scale structure from the galaxy observations. And here, I want to emphasize the importance of the Sumire effort led out of here in Japan, where IPMU is playing a major role at Subaru, where we're already getting this fabulous data from HyperSupremeCam. If you just again advertise that wall at IPMU, the data is incredible. I actually now have 2 HSC images sitting in my house because they're just so great. You can just see this tremendous detail where you really see the galaxy fluctuations, infer from that the overall matter fluctuations, Looking at HSC, you also realize how awesome LSST will be and how scary the LSST data is. Because when you get down, when you look at the HSC ultra deep data and you realize LSST is going to have that much data over the entire, much of the sky, and all the galaxies are overlapping, and it's going to be an incredibly rich data set. And I think with HSC, I hope we will have the control of systematics with its high resolution to have a really definitive measurement from the ground on sigma 8. And I think that's coming, and we're excited about. I want to also advertise WFIRST for two reasons. One, I think it represents, we hope, so the ultimate, in the coming years, dark energy measurement using a number of different techniques, lensing, baryon-acoustic oscillations, growth of structure, supernova observations with really high precision photometry to go after dark energy. But I also want to use this as an opportunity to advertise an upcoming meeting that we'll be having here in Japan. We are hopeful that JAXA will be joining, Japanese community will be joining WFIRST. Part of that will involve 100 nights of Subaru observations to complement the WFIRST observations. There's going to be a meeting in Mitaka. Do you remember the dates?
18th from 18th to 20th.
So we think December 18th to 20th, where we will, I will be back in Japan for that event, and we hope to, for those of you interested in potentially getting involved in WFIRST, the plan will be, if Japan joins as a partner, that Japanese scientists will be able to join. There's actually, besides the cosmology, many other science teams associated with WFIRST, and we're hoping that people here are interested. So let me conclude. I want to leave you with the sense that this has been a very exciting time for cosmology. In some ways, we seem to have converged on a standard model which describes lots of observations. But while we've converged on this model, it's a model that has profound open questions. We know we need new ideas for dark matter, for dark energy, for inflation. And it's also a situation where perhaps we're seeing a little problems in this convergence. And at this point, it could all turn out to be systematics that we need to understand better. But this may be, I'm old enough to remember when we had these systematics in large-scale structure that we were sure would go away because a cosmological constant was just too awful to contemplate. I feel the same way about W less than -1, and I'll leave you with what I said when I was interviewed by the New Scientist November 1st of last year. When I was asked about the Big Rip, I said, to me, the Big Rip is like the Trump presidency. Frightening to contemplate, physically perhaps possible, but I'm convinced it's not going to happen. So thanks.